Hello, my name is Hanah Greengard, and today I'll be talking to you about the research I did this summer in Dr. Arando's lab here on the WashU campus. My research concerns X-ray telescopes, so today I'll be talking to you about what they see and how they work. To set the scene, an important concept with looking at faraway objects in space is that when we look into deep space, we are looking back in time. This is because light takes time to travel from one place to another, and so we see faraway objects like black holes as they were at the time when they released the light that then traveled many light years to reach us here on Earth. Astronomers can therefore look further back through time by studying progressively more distant objects. So we're limited by our current technology, which includes space instruments like Chandra, which is an X-ray telescope that's currently in use and in orbit. One area of interest that astrophysicists have involves supermassive black holes that date to the beginnings of our universe. With current technology, we are unable to formulate strong hypotheses concerning these supermassive black holes because we're simply unable to collect enough data about their origins and growth. Our hope is that if we develop more precise instrumentation, we can learn about their early stages, which will better enable astrophysicists to study the beginning stages of and developments of entire galaxies as well as the universe. So as I've mentioned, black holes are something that X-ray telescopes look at, and what they're actually going to be looking at is the jets of a black hole. In these jets, there's synchrotron radiation from electrons moving at a significant fraction of the speed of light in helical orbits around the magnetic field line, and the synchrotron radiation is actually what is producing the X-rays that we can observe with our telescopes, such as Chandra. And so that's how we collect the data with our X-ray telescopes, but we still need to know how to analyze it so we can understand trends of sources over time. Part of this process is going to be running the necessary software, but for each new source, you will also have to do a few extra steps. This includes identifying the source region and the background region, and this is an image that shows that process. The source region you will need to identify within this small green circle, and the background region would be a larger circle that is around the source region that does not include the source region, essentially the backdrop of the sky outside of the source. And you do this so that you can extract the spectra from this image and then run the rest of the program to create the finished graphs. This is an example of a finished graph, and so I'll explain what the axes are now. The x-axis is going to be the energy in kilo electron volts, and what you see with your eye is actually going to be 1 kilo electron volts, and this middle of the graph is about 1,000 times that. The y-axis is going to show how many photons there are at different energies. The bottom graph shows how much the data deviates from the line of best fit that we've plotted on the top graph. And we can use this by looking at the spectral index that's generated by the software and compare it to other years for the same source, and then evaluate trends over time. For example, if it's brighter in a given year, that might mean that there's more accretion, which is matter falling into the black hole, or maybe the way that the electrons are colliding with each other in that particular layer is accelerating the particles and producing more energy, leading to bursts. And so to explain how telescopes capture X-rays, you need to understand what the grazing incidence is. And that's just shown here, where the incoming X-rays are hitting the mirrors at an angle that is very close to parallel. They need to do so because if they hit at an angle that is more head-on, the X-rays have so much energy that they will actually just go through the mirrors. And so X-ray telescopes concentrate the light from an X-ray star into a focal point, and that allows us to examine and process the data like what you saw on the previous slides. And so to increase the effective area while making sure that these telescopes are cost effective, the mirrors for future telescopes are going to need to be less than 1 millimeter thick. This means that they're very fragile because they are so thin, and therefore they're going to deform when they are assembled. We want to be able to correct these deformations while the telescope is in orbit. One way that we think we can do this is by keeping some small amount of current running through the mirrors, and that's what our lab is actually investigating. And so what we have here is one of the mirrors that our lab has made, and these are the electrodes on the back of it. What we will do is connect the voltmeter to these electrodes, check the resistance of the mirror, run some current through it, and then check the resistance again, hoping that the resistance has gone up. We can also use the Shack-Hartman wavefront sensor's software to image the surface of the mirror. This is an example of what a graph might look like from the software. This is the corrected wavefront, and what you can see here is that the bottom of the mirror is closer to us than the top of the mirror from the color gradient of the mirror on this graph. And so what we want to do is align the mirror, and then we'll know that our mirror is aligned properly, the readings are stable, and we can then look at the software to see what the deformations look like for the mirror. This is what our setup looks like in our lab. We have the Shack-Hartman wavefront sensor in the bottom left corner, the parabolic mirror, and the X-ray mirror connected to its stand. And so the Shack-Hartman sensor consists of a detector with an array of lenslets in front of it. Each lenslet is going to be focusing a portion of the pupil to a spot on the detector. For a flat mirror, the image is going to be like this perfect grid of dots. And on the right, you can see we have this circular mirror where some dots are smaller or stretched. And this actually is going to be indicating that the surface is not flat. And so Our research aims to develop mirrors that are thin enough for the X-ray telescope, but can also be fixed in orbit when deformations occur from the construction process. Ideally, our experiments would allow us to refine a process that allows people to overcome this obstacle when constructing the next generation of X-ray telescopes. If we succeed, we can look further back into the past of our universe by discovering more info about high energy sources in our universe with this next generation of telescopes, which would include the LINX telescope, which is a project that has been proposed already. Thank you very much for listening to me today.